Okay, thank you, Yuval, and thank Tufik, and thank all those involved in the organization. I know it's a lot of work. So this is joint work with all these smiling faces that you see. It's about intersections of matroids. I guess I am assuming that everybody knows what a matroid is. It's a hypergraph that is closed down, and the maximality for its maximality of an edge implies maximum size, and this should be also hold for induced subhypergraphs. Why is it interesting? Well, I guess everybody knows that this is a very basic tool in combinatorics, and let's me just see why doesn't it move. Okay. And I will use another terminology for hypergraphs. I'll call a hypergraph, I'll call it complex. This is the name that topologists use. And since we're going to use topology, I'll stick to this name, complex. So complex is a closed down hypergraph. Every complex has a geometric realization. You put points in general position. And if there is an edge ABC, you fill the triangle ABC for every edge you do that. Another terminology that we should use, the rank of a complex is just like in matrix. The rank is the maximum size of an edge. And an observation that I didn't know before I started, although it's a very trivial observation, I didn't know that every complex is the intersection of matrix. So here is short proof. Defined for set E, let ME, M is for matrix, of course, is all the sets that do not contain E. And then if you have a complex C, then this ME is easily seen to be a matrix for every set E. And the intersection of all MEs for every E that is not in the complex is C, just an exercise in set theory. Here's an example. So the left guy is not a matroid because this singleton point is maximal with respect to containment. You cannot add anything to it and still remain in the complex. But it's not of maximal size. It's of size 1, and there are in this complex, as you see, this, I don't know if you see, yeah, you see this is an edge, means this pair is in the complex. So then rank is 2, and there is a maximal size, maximal set of size 1, so it's not a matroid, but it's the intersection of 2 matroids. Here they are. These 2, if you intersect them, you get this guy. These are easily seen to be matroids. Okay. So the question is, so every hypergraph, every closed complex is the intersection of matrices. The question is how many? And if it's the intersection of K matrices, you want very few. The fewer, the better. If it's the intersection of K matrices, you call it belong to min K, matrix intersection K. Okay. And what we would like to see is what are the properties? What can we say about min K matrix hypergraphs? So the story starts with this guy, which you may know. This is Dennis Koenig, and he proved the theorem, Koenig's theorem, which is more or less all theorem. They're more or less the same. We'll define for any hypergraph nu of H, the maximum size of matching set of disjoint edges, and tau of H is the minimal size of a cover. A cover is a set of points meeting all edges. And the theorem of Koenig is that in a bipartite graph, tau is nu, so they're the same. And as I said, this is more or less Hall's theorem. Here's a conjecture that's played an important role in the paper that we wrote. I'll tell you only a very, very small part of this paper, the part that uses topology. And in the paper, it serves some interesting role. Here's an interesting conjecture, riser, that the generalization of Koenig's theorem to higher dimensions. So you have an M-partite hypergraph. The conjecture is that the covering number is no more than M minus 1. You know, for M equals 2, that's the Koenig case. You get here 1, so tau is at most nu, tau is at least nu, it's trivial, so tau is nu, so M equals 2, you get Koenig's theorem. The next guy that's contributed here, that's the major contribution here into our talk, this guy. May recognize him, Jack Edmonds. And he realized that Koenig's theorem is a special case of general theorem matrix. So here is the definition. If you have M matrices, nu of those guys is the rank of the intersection. Here comes the intersection, from the intersection. And there is tau. Tau is the minimum of the sum of sets AI that together span all vertices in the world. Span A1 spans in matrix number 1, A2 spans in matrix number 2. And if you take all these spans, they should cover S. The minimal size of this set, sum of sizes, is called tau. And so this is cooperative spanning. And Edmonds generalized Koenig's theorem to two matrices, only two in this case. Nu of M1 and M2 is tau of M1. You don't have to remember, we're going to swerve from this swerve away. Here's the conjecture. That's the generalization of Koenig's, of Reiser's conjecture. Tau of M matrices is at most M minus 1, gain 1 here, times nu. There is we know very little about this. What we know is the case of M equals 3, which is a theorem by Berger and myself. And we should be interested mainly in colorings of hypergraphs. What is a coloring graph? It's a cover by edges. So a coloring of a complex C is a set of edges covering together all vertices in the world. And chi of C is the minimal size of a coloring, minimal number of edges that cover together all the vertices. Now you may be surprised a bit that chi is usually reserved for something else. In graphs, it's a coloring number of the graph. A coloring of the graph is a covering by independent sets. So if you look at the hypergraph of independent sets, then this notion is just precisely the ordinary coloring number of graphs. And S in graphs, there is a list coloring number. So you're not allowed to choose any color at any vertex, but every vertex has a list of colors. This list colors. Every vertex has a list of colors that it can use, and it's not allowed to use any other colors. A list coloring is a choice for every vertex from the allowed list that it has. And in the case of hypergraphs, if you think about this graph case and the independence of complex, what you want is that all vertices of the same color that you chose, you colored by choosing a color from every list, and you want that every color that is chosen in an edge of the hypergraph, which is independent hypergraph. It means that the colors, the vertices of the same color, form an independent set. Yeah? So it's just the usual notion. The list, so I did it right. What is the covering number? Yeah. Now, the covering number is the minimal size of the cover, and the list coloring number, call it chi of L, is the minimal number that if all lists are of that number, smallest number k, such all lists are of size at least k, you're guaranteed to have a coloration, a list coloring. Okay, so this talk is about really the relation between chi of L and chi. The list coloring number, which is obviously larger, you restrict yourself. So chi of L is at least chi, and the question is how large. And here are conjectures. One conjecture is that the two are equal for line graphs. Okay, and this was proved by the bipartite case. Okay, and here we go. We plunge into our topic by theorem of Seymour. Theorem is that in a matroid, chi L is chi. List coloring demand the same number of says number of colors. Okay. And then came Berchi, Schwartz, and Yamaguchi and made two conjectures. One is that if your hypergraph is in mean to its intersection of two matrices, then chi is chi L. This coloring number is the coloring number. We have no idea how to that should be D because it's even the bipartite case is no, it's not. But even when the two matrices that whose intersection is H are partition matrices, that's a very special case of matrices. If they're both partition matrices, then it's known by the theorem of Galvin. It's hard. It was open for a while. So this is quite hopeless. But the second conjecture is hopeful in some sense. So the second conjecture is that if you're in mean K, if you're the intersection of K matrices, then your chi L is no larger than some constant dependent on K times the coloring number. The ratio between them is dependent only on K. Okay? So this we know how to do it. The theorem to prove is that if H is the intersection of K matrices, then the ratio between chi L is no more than K. Chi L is at most K times chi. The truth is probably much smaller than K, but we don't know. We know only K. And this is what we're going to prove today. I'm going to do something not quite common, is really give a proof. Why is that? Because we'll introduce the topological method, and I think it's worthwhile knowing the basics of the topological method. Okay, so here we're plunged into topology with the notion of connectivity. What is the connectivity of a complex? So the connectivity, which we denote by eta, is the minimal dimension of a whole. So, for example, if your complex is a cycle, then the whole is the middle of the cycle. The dimension is 2. The dimension of the boundary is 1, but the dimension of the inside is 2. So eta of a cycle is 2. How about eta of a disconnected hypergraph like here? Do you see here a hole? Yes, of course. You see here a hole. The rectangle here is the hole. The dimension is 2. The question is there a smaller dimensional hole here? And the answer is yes, here it is. This is a hole. What is a hole? It's the boundary of a sphere. This is the boundary of the hole is a sphere, boundary of the ball. So this is the boundary of the segment. So it's this is what is called S0. S0 is a disconnected. It consists of 2 points, and this is a hole. And it's not filled. You see, it's a hole. Fill a hole means that it's not filled in the complex. Here, if I want to fill it, I'll have something of dimension 1. So the dimension of the hole is 1. So the connectivity eta is 1. So please remember, eta of a disconnected hypergraph, disconnected complex is 1. Okay. Here is what Whitney had to say about the connectivity of a matrix. The connectivity of the matrix is its rank, or in the generative case, it's infinity. Okay, and then Eli Berger and I generalized it for intersection of K matrices. If you are the intersection of K matrices, then eta is at least the rank divided by K. Okay. This is one of the tools that you should use for the proof of theorem. Okay, now a basic definition in topology is the join of two complexes. We have here two complexes, C and D. The join is you first of all separate them and put them on disjoint sets, disjoint ground sets, and then you look at all the unions, edge from an edge from C and an edge from D, take their union, and all these unions form a complex. This is the join of C and D. Here's an example. So C is just these two disconnected points. C is disconnected, the blue guys. And D is the red guy, the gay, disconnected. C star D, the join, is this. You put these two guys in C and put these two guys in D and take all unions, all possible unions, all four unions, and you get a C2. Okay. Now notice something important. These two were disconnected, namely their eta was 1, if you remember. And here you got the join as eta 2, because you see the hole here in the middle is of size dimension 2. So eta of C times D, C join D, is 2. This is no coincidence. It's always true that eta of the join is the sum of the eta. Okay? Eta is additive with respect to join. This is going to be serve a very important role in our proof. So, okay, it's not precisely. I'm not trying to be precise. Eta of C join D is not necessarily here. Perhaps here it is. It's not necessarily the sum. It may be infinite. Degenerate cases. There are degenerate cases already. Okay, the other tool which we're going to use is topological hole. Topological hole is the following. You have sets, V1 up to Vm, let's say, and there is a complex on them. You don't see it, but there is a complex here. So a hypergraph. And what you want is you want to choose, like in Hall's theorem, choose one from each, one representative from each, and what you want is that the set of representatives will be in your complex. So there is a complex, not explicit here, and you want your choice of representatives to belong to the complex. This allows much more general setting than Hall's theorem, the original Hall's theorem. And here is the whole topological. I didn't say it, but you must understand that eta is the right, in topology, the right notion for size. You replace size by connectivity. That's the real. So I'm going to write here something that is very similar to Hall's theorem, where size is replaced by eta, by connectivity. We should return to it. Size is replaced by eta. Okay. So the theorem says this. If you, for every k sets Vi, J column, capital J, sets Vi, if the eta complex induced on them is at least J, just like in Hall's theorem, in Hall's its size is J, then there is a C transversal. C transversal is what I wrote here, a set of representatives that belongs to the complex. Okay, so that's the topological hole. Let me repeat it. If every K colleagues sets here have eta at least K, then there is a C transversal, namely a set of vertices, choice from vertices, from each edge, from each Vi, choose one point, and you want the representatives to form an edge belonging to the complex. Okay? What I have here now, this is, I cannot, you cannot see what's written here, you have to read it. So here is the V1 and V2, and the complex is just consists of these two pairs, this pair and this pair. Is there a C transversal? C transversal is a point from here, a point from here, and you want these two together to be in the complex. No, these two are not in the complex. So the complex is just the geometric realization. It tells you that the complex consists of this pair and this pair. This is not in the complex. So you cannot choose here a C transversal. Indeed, look at these two guys here. I'm claiming that the hold condition does not hold. Indeed, the eta of the union here, the union is disconnected. You see, there is no way to get from here to here. So eta is 1, which is less than 2. You want them to be 2 for two sets. You want them to be 2 in the Hall's theorem. So the topological hole is not, the condition is not valid. So is not obtained. So there is a chance. This is not an if and only. Topological whole is not an if and only if. It doesn't mean for sure that there is no C transversal, but in this case, you see, indeed, there is no C transversal. Okay, some definitions. Delta R. R here is for rank. Delta R of C is the maximum of over all sets S of the size of S divided by rank. Now, what is the meaning of this? It means that if you want to cover S by sets from the complex, each of them is its most rank C divided in S, which is equal to S, then you need at least this number, at least delta. So chi is at least delta R, okay? If every set is of size at most rank, then you need to cover a set of size S by this quotient at least. So this is what's written here, that chi of C is at least delta R, okay? And as I told you, rank is really should be replaced by eta. So this is really the right definition, delta eta. Delta eta is the same, but size replaced by eta. Okay. And okay, so here's an observation that if C is the intersection of K matroids, then delta eta is at most K delta R. This is something that I said before. I said before that eta is at least the rank divided by K, if you are in mint K. Remember, that's the theorem of Eli, Berger, and myself. That eta is at least rank divided by K. So if you put it in the definitions of delta eta and delta R, you see that this is what it means. The delta eta is at most K delta R. Oh, here, and I wrote here the reasoning. Okay, so we have this to serve us. And I haven't reached the core of the proof is this one. Chi of L of H of any graph. C is H. Okay, sorry. So chi of L of C is at most delta eta of C. So remember, chi of H, chi of C is at least delta R. And it's at most delta eta. This is one. And the nice thing here is that in this theorem, don't have to differentiate between chi L and chi. It's true for chi, this thing, it's true for chi L, as you will see. The proof is indifferent to lists. So you don't care. If you can allow the list version and you have the same theorem, chi of L is at most delta eta. And this is going to be to use topological call. This is where topological call will do. But suppose for a second that you know this. Then you will finish the proof. Why? This will complete the proof that chi L is most K chi, because then we have the following. Let's see. We have a list, a chain of inequalities. Delta R is at most chi of Z. We said it. That's, we said it's about the quotient set divided by maximal size of the set inside of set complex H inside. Okay, so this we mentioned before. This is a triviality. Yeah, always the list coloring is harder. So you need more covered and more colors. Okay, this I promised you. It hasn't proved. And now, if you remember, probably don't remember, but I'll remind you, this, the right one, divided by the left one, is at most K. Okay, this is the theorem of Eli and myself, that eta is at least rank divided by K. If you're in K. Okay, this, I mentioned it before. So this divided by this, the right divided by the left, is at most K. So if you have these equalities, then of course this divided by this, chi L divided by chi, is of course at most K. Even the rightmost divided by leftmost is K. Then inside, of course, which is the theorem that we want to prove. Chi L is at least, and the chi L is at most K times chi. Here, the ratio here is what we want. Okay, so what I owe you is this, that chi L of a complex is its most delta eta of the complex, assuming that H is C. Okay, and this is true for every, you don't need any condition C. Okay, and here's the proof. So this is the theorem, I repeated it. And here is the proof. I make a table. On the row, and each column corresponds to a vertex in your world. And each row corresponds to a color in the world. You can guess what, for example, the fact that these two guys here, this guy and this guy, what do they mean? This means that color 2 appears in the list of V1, and color 2 appears also in the list of V3. So V3. Okay, this is the incidence matrix, if you wish. Okay. Okay. Now, what we want to prove is that, let me see, perhaps it's better. Okay, let Q be delta eta. And the claim is that if every list here, the list is, the list of V1 is all the red guys here. Oh, mistake. The list of V1 is all the red guys that you don't see here because I'm too lazy to write many of them. Okay, so there are Q of them because I assume I want to prove that chi L is at most delta eta. That's so if Q is delta eta, I want lists of this size, list of size K, Q. And here are the list of size Q of V2, here of V3. And what do I want to do? I want to choose from each VI one of the labels here, of the red ovals here, so that I'll get eventually every color is in C. I want those chosen from color 2, I want it to belong to C. Okay, that's the condition on a coloring, list coloring. List coloring means I want each VI to choose from the list, so that every color is in C. Okay, so that's what I want. Which is precisely C transversal for what? It's transversal for the join of all these rows. I want the guy in this row to be independent. I want these guys that I chose in this row to be independent. Each separately. Each separately means that this is a join. Okay, so I want there is a join of these guys, of this C restricted to this, join C restricted to this, join C restricted to this, and I want my choice to belong to this join. And of course, what I'm going to use is the topological hole. So what I want to do, okay, first of all, a remark for what I want to do. If delta eta is Q, then for every set, eta is at least QX. That's the definition of Q. It's the maximum of X over delta X. Okay, that's the definition of delta, maximum of X divided by eta. So if delta is Q, then eta is at least QX. Okay, that's an observation. Now let's return to our table. So what I want to show, topological hole tells me, look at a set of columns, which are for laziness sake, I just drew it here. It's 4 columns, the yellow columns. These are the yellow columns. I want to suppose I chose 4 columns. I want to show that eta of the join, as I called it before, eta of the join of the complexes, this complex, so forth, must be at least in this case 4. There are J columns. I want the eta to be J. Okay. And now as I wrote before, every row has eta of the complex. At least here it's not good. It's not Ri, it's Ri restricted to J. I'm going to look just the yellow part. So Ri means here really, Ri is the row I. We have seen the row I, but only in these 4 columns. Okay, so this is this is our world already. So we have to show. Can I get these pictures on the right? Perhaps this. I don't know. Ah, here it is. Okay. So you won't see my new nice face, but you can see the math. So the topological whole tells you that you want for every set J of columns, the eta of the join at least number of larger every J. Then there is a choice of there is a C transversal. There is a choice of the representative that belongs to C. Okay, so this you wrote before. Eta, this R, and here I didn't forget the J. Eta is at least Q. Q is delta, if you remember. Okay, Q is delta, so eta is at least delta times the psi. Now, by additivity, the eta of the join is the sum of the etas. Remember? So eta of the join is at least, it's not equal, it's at least, the sum of the etas, and the eta of each guy here is at least this guy. Okay. So sum of these guys divided by Q, it's now remember every column has Q red points, Q a list of size K, Q. Okay. So if you look at the sum of all of these guys, it's every column has Q, you have J columns. So together you have JQ. You have to divide by Q and you get J. So this is precisely what you want. You want that the eta of J columns is at least J. And we have, so by this we have the transversal, C transversal, and this is what we wanted. This gives you a coloring, so show that if the size of each column in the table there is Q, then there is each column here sees Q red guys. Okay, then there is a C transversal, which is what guarantees the coloring. So what we did here is we translated the coloring number to a C transversal problem. I don't know who invented this transformation. It's very well known. The first place I saw it was the book of Welsh, the matrix theory. Perhaps he invented it, I don't know. Okay, so we proved that if Q is delta eta, then there is the list of size Q are sufficient, which is what we want. Chi L is at most. Now, where did the K come from? Forget. Where did the K come from? I don't know. K is not relevant here. I'm just proving the theorem here. This theorem. That the K is long ago gone. K doesn't appear here. We just proved this. Okay, I assumed that all this will take me explaining. Okay, it's not too bad. I didn't use all my time. Let me just tell you a bit about what else in that paper. What I liked most is the generalization of work of Edmonds on polytopes. So some of you may have heard that Edmonds defined for every matroid, actually for every complex, a matroid which is, again, for every complex, he defined a simplicial polytope, and the polytope consists of the convex hulls of the edges, as represented in the geometric representation of the complex. And the beautiful theorem of Edmonds is that in matroids, it's true for matroids, the complex of the intersection of the matroids, of two matroids, is the same as the intersection of the complex of the again, polytope. The intersection is the intersection of the polytopes. And this is even stronger than it implies easily, vice versa, it's not true. It implies easily his theorem. Remember the generalization of Koenig's theorem. And we are interested in the intersection of more than two, not necessarily only two, so more than two matroids. And you can guess what is the conjecture. The conjecture is that polytope of the intersection is, if you multiply it by, k, if you have k matroids, and you look at the intersection of these matroids, then the polytope, if you multiply it by k minus 1, it will contain the intersection of the polytopes of the individual complexes. This is a really nice conjecture. Okay, so just going back to this, the Reiser's conjecture, this is the generalization of Reiser's conjecture in polytopes terminology. Okay, I ended quicker than I thought. I don't think that anybody will protest. So thank you very much.